All right, can you all hear me okay?
Yes.
Okay. So what I want to do this morning is answer questions you have in a scope lab and a motor lab, and I'm going to talk about motional EMF. So I'm going to continue the discussion that I had on Tuesday on chapter 31, but I'm going to leave some for the lecture today too at 2 o'clock. I kind of just discuss motional EMF, and then we'll do some examples in class today and some demos. So do you have questions on the scope lab quiz or whatever you want to call it? Or concerns?
So just to confirm, it's supposed to be set at 5 volts?
What's supposed to be set at 5 volts?
The power supply for the generator?
You mean plugging the power supply to, I'm not sure, the voltage that you want out of the scope, or the voltage you want to put into the generator?
The voltage you want to put into the generator.
Yeah, it's around 5 volts. I just use USB plug, right? I mean, I just plug it into my computer.
Oh, okay.
All right, it says 5 volt. It should be 5 volts. So it has a range from 4 to 10. So probably I don't want to play around with it too much. I just use the USB on my computer.
Okay.
I mean, there are, I don't know if you have them, you know, you have those USB plugs that you can go from 120 to the USB. I'm not sure if you have anything like that. But usually my computers are closer, so I just connect to my computers.
Oh, okay.
Yeah, and that works fine that way. They're not the best, okay, so they're not the best signal generators. I've had one go bad on me. I had one go bad on me last semester, and I don't know why. It would turn on, but then the buttons wouldn't work. So, I mean, this is $30, right? I mean, so you kind of get what you pay for. A good one that would be used for a labs probably costs $400 to $500. So you'll notice the issues in the upcoming lab. Actually, I kind of tried to choose components for the next lab so that you won't have the issues we had last year. But because of the fact that it can't really drive much current through a circuit, it will have problems, especially when we use low valued resistors. We're really limited as what we can do with the equipment we have, so I do have problems with it. Next semester, next fall, I will do these labs on campus, so we will use the good equipment. I'm not going to have those problems. Other questions?
Is there any chance you can show your motor that you made?
I don't have it with me, unfortunately. I mean, I have, I mean, if you look at the videos, the original video for the lab, I showed you 3 different motors. And you can take a look at those. If you go to the YouTube channel, although, you know, I didn't do a good job labeling the labs, you can look at, you know, if you're on my playlist, I do have the lectures from the fall, and then I have different examples for those. If it's not working, I guess the question, what is your question regarding? Is it not working, or do you just want to see an example?
I just wanted to see an example.
Did you see the video in the discussion board?
I'd have to check.
Okay, so why don't you look at that, because there's an example there too. It's not from our class, but it's somebody building it. So let me take a look at a question in the chat. So Jacob, so yours stopped spinning after a while. How many batteries are you using for your motor? Can you buy 2 more and try it? So you have 4? I mean, ideally you want to do it with 2, but try to get 2 more and see if it runs with 3 or 4. And then, so because if you can see it running with 3 or 4, then you know that you just got to make some adjustments. And really the adjustments that you would have to make are making sure you have good contacts so you can measure. Yeah, so that power supply at 6 volts will probably not give you enough current. Because at 6 volts, you'll probably be above 5 amps. I think that power supply that came, I think is 30 watts. And that wouldn't go over 6 volts anyway because you might melt the enamel on the magnet. So I really think it's better if you use the 4 batteries. Yeah, more batteries is the better choice, but just go up to 4, don't go above 4. I think that power supply that comes with the boards would probably be okay, maybe up to 4.5, maybe 5 volts. It just depends on how much current you're drawing. So one of the things you can do is measure the current through your motor. You got to use the 10 amp scale on your ammeter. You won't blow a fuse there because the 10 amp scale, it has no fuse, which is not a safe thing. But and then you can see as the motor rotates, what do you see for the current? I mean, it's going to change as the motor rotates, but if it stays at 0 a lot, then you know you have a contact problem. And then also make sure the orientation of your commutator is correct, because you want the current to change directions when the torque on the armature is 0. Okay. Okay, so if the electromagnet is getting hot, how many batteries are you using, Nicholas? 2, and the electromagnet is getting hot. You know, Jacob, what you can do is, can you send me like a brief video to show me what you have? And then I can take a look at it offline. Okay. So Nicholas, measure the resistance of the wire between the 2 ends for your electromagnet. Make sure it's not 0. And do that for the armature too. Oh, I misread your chat. Sorry, Nicholas. I thought you said it was getting hot. I thought it said the electromagnet was getting hot. Sorry. Oh, it is getting hot. So Nicholas, that indicates a short. The fact that it's getting hot. So yeah, so measure the resistance of both the electromagnet and the armature. Make sure that the orientation of the commutator is correct. And again, you can send me a short video of what it looks like, and I can use the next couple of days to take a look at it. You just make sure that the video is clear so I can see all the contacts and everything. Okay. And then I can make some, hopefully I can make some suggestions. There is, the fact that yours is getting hot, Nicholas, concerns me because you might have a short. So I wouldn't go to more than 2 batteries yet. And then, you know, make sure you folks look at the discussion board that I have on Canvas, because I have a video where someone actually builds it. Okay, it's the same motor as you have. Look at the tips that are on there. Go, just make sure you look at the discussion board, okay? Because there's an actual video of somebody building the motor that we're building. If you go online, you can probably find other YouTube videos where people are building different versions of the motor. Okay. So try to use the resources that are that I've given you. So what is the one that you sent, Christopher? Let me see.
It's one, he's going like step by step, but it's like 45 minutes long.
Oh, that's a long video. Is it captioned?
Okay, no. Up to 1,000.
Yeah, and that's a good one too, actually. In fact, students, he's got bearings in his, right? I'm just looking at it.
I think so.
Yeah, I can, Damien. After I'm done lecturing on the material, I can answer your question on the BIOS of our worksheet. Yeah, actually, you know what? Chris, that's a nice video. I should probably email it to everybody. I mean, it's different from what we're using, but it's still a good example of how to build this motor.
Yeah, it's just the idea.
Yeah, I know, I like that. The only problem is I can't put it on modules because it's auto captioned instead of having a regular captioning. But I can always email everybody this video. So that's actually good. Because I've actually had students build one like this. As long as the armature is 1/4 inch in diameter. And everything's hooked up in series. Okay, there's a question in my the video. Just 1 second. So in the video I put on the discussion board, look at the description of the video. Okay, Jacob. He talks about the hardest part of building that. What I like about it is, you know, that video I put on the discussion board that the thing runs on 2 batteries. And he's using like 12 or 14 gauge wire for the brushes. So that'll give you an idea of what, if you use just the parts I gave you, what it kind of should look like. And he did use different nails. You can use different nails for these motors. So you can buy new ones if you want, but you got to make sure if you use different nails, they got to have iron in them, because if they don't have iron in them, then you're in trouble. In fact, in the motor that you see in the description, but those nails are huge. I'm looking at it right now. It's only a 1 minute video. But then in the description, he talks about the issues he had. Other questions on the motor? Now, granted, there's only, what, 4 of you? There's not that many of you guys here this morning. Let me see.
All 7 of us.
7 of you, sorry. The first time I saw 4, okay, so there's 7 of you. Yeah, it'd be nice if there were more people be reaching with this video, but yeah, like I said, if you're having trouble with the motor working, first of all, with the motor working, just send me a video. If it's not working, if it's working but you can't get it down to 3 volts, the big one is getting consistent contact. The other big one is making sure your armature is wrapped symmetrically. Anything that's asymmetric is going to cause wobble, and if it wobbles, then it's going to slow down. Okay. But that video I have in a discussion board, that his motor runs at 3 volts. And his armature is bigger because he's actually using much bigger nails. I can try to look for, I'll see if I can look for one of the videos from last spring, because I had a motor that ran on 1 battery, if I remember correctly. If your motor runs at 3 volts and it spins fast, I want you to try it with 1 battery. So Jacob, and I'm not telling you exactly specifically, but all I want to say is, Jacob, that you want the current, you want to orient your commutator so that when the current switches directions, the torque on the armature is 0. You do not want the current to switch directions when the torque on the armature is maximum. In other words, if your commutator is rotated by like 90 degrees, it ain't going to run. So I guess the question is, when is the torque 0 on the motor? Can anybody tell me when the torque will be 0 on the motor? Other than when the current's 0, right? There's going to be an orientation where the current is non-zero, but the torque is 0.
Does it have to do with what plane the motor is oriented in relative to the current?
Yeah, I mean, look at your armature has loops of wires, right?
Right.
So I'm going to draw the loops of wire for the armature. I'm going to draw it like this. And the normal to the loop is this way, right? This is also the direction of mu. And torque is mu cross B. The torque is 0 when mu and B are parallel to each other.
Right.
So when your magnet is like this, essentially the magnetic field is either this way or that way over here, right?
Yeah.
So when your armature is like that, then the torque is 0, right?
Right, regardless of which way the field is going.
That's when you want the current to switch. When the armature is like this,
Then it's maximized, right?
yeah, because your normal's this way, the magnetic field's that way. So that's when you want current there. Because it reaches this point, you're in trouble. It ain't gonna spin. Okay? So that, Jacob, is what I was saying about the commutator. So if you have the commutator oriented incorrectly, it ain't gonna work. Okay, so what I want to do then is talk a little bit about a topic called Motional EMF. It is another example of an induced EMF, but for a different reason. Okay, so we want to look at this. And so what I want to do is set up the following system. Suppose I have a rail. And I have a magnetic field that points into the board. It doesn't matter whether it's into the board or out of the board, but for our purposes, it's into the board. And I'm going to put a conducting rod in between here, the rails. The principle of the railgun, essentially, but kind of. We have to have a power supply here. We'll talk about the railgun later today. So let's say this has a resistance, and so just to indicate that we have a resistance, and it doesn't matter how I draw in my resistor, let's say I have a light bulb here. I like the light bulb because then, you know, it'll go on if I have a large enough voltage. And let's say that the rod is moving to the right. Okay? And remember Faraday's law. Faraday's law says this, that the induced EMF is minus the time rate of change in the magnetic flux. And you know, this is determined, deduced from experiment, right? That's deduced from experiment. You can't derive this, okay? It's called Faraday's law, but several people were involved with this. I mean, the minus sign is due to Lenz. Okay, and Joseph Henry in the US was also involved in this. So what's happening here? What's happening to the flux here? As the rod goes to the right. Is it changing?
No.
But isn't the area increasing? Aren't there more field lines going through the loop as this rod goes to the right?
I guess. I actually have no clue.
But what is flux?
It's like the amount of field lines that are entering minus the amount that are leaving.
Yeah, so when it starts here and it's somewhere down here later, aren't there more field lines going through?
I guess I don't see why.
Okay, I'll draw the picture. So here's force. So these are the number of, these are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12, these, each one of these represents a line, right?
Sure.
Okay, so now when I move the rod here,
So the field beneath and to the right of the rod doesn't contribute to it? Is that what we're...
yeah, because this is the loop we're talking about. Let's say this side's open. This is the
Okay,
closed loop.
Gotcha.
This
Sorry,
is
I didn't understand that part. I assumed it was just going on, but we didn't draw it in.
oh, you mean this other side?
Yeah,
This is the part of interest because this is the area enclosed by the loop, right? This is the loop.
totally.
And this is the area closed. So isn't the area enclosed by the loop increasing?
Yeah, it is.
So there's more field lines coming, going into the board.
Yeah.
So this is changing. So that means there is going to be a voltage drop. Right? There's going to be an induced EMF in this particular circuit. And it's going to be to this moving rod. This part's not moving at all. Okay? Well, we want to look at the mechanism. We want to focus on the mechanism here. Because everything I talked about on Tuesday had to do with a changing magnetic field, right? Here the magnetic field is uniform. And so we're going to have a different mechanism. We're going to have the same effect, and we're going to have a different mechanism. We will have two mechanisms that produce the same effect. That's what's unusual about Faraday's law. So let me draw the rod. And there's a magnetic field into the board. I didn't draw that very well. There's a magnetic field into the board. Of course, there's electrons in here. If I use the right hand, right, the electrons are free to move in that rod. What is the direction of the force on the electrons?
Is it downward?
It's downward, right? So the magnetic force is downward. And so if I draw in an electron, the electrons are going to go downward. They're going to drift downward. So according to us, the total velocity of the electron is going to look like this. Right, relative to our frame, the electrons are going to be going this way. This is the actual velocity, but it's this that I'm interested in here right now, because what's going to happen when the electrons drift downward into the rod? Right, they're going to move downward in the rod because they can't move past this point. You're going to have a separation of charge here. You're going to end up having positive charge here, negative charge down here. That's going to produce an electric field that points downward, which means an electric force upward. And so these charges are not, I mean, these things initially are accelerating very quickly, and they stop accelerating when? Well, we got to use the Lorentz force, right? The Lorentz force is this. The acceleration stops when this goes to 0 and E is equal to that. Then after that, they move at constant velocity. So the charge will start accumulating on these ends, but because this is connected to the rail, the charge will start circulating. And so what you'll end up getting is a current like this.
And to clarify, the current pointing that way is just because we point in the direction where positive charge accumulates?
Yeah, because I'm using conventional current, right? Because if the electrons go this way, the current goes in the opposite direction.
Right, I just wanted to make sure, yeah.
Yeah, you're right. I'll show you one more slide. Okay, so that shows you everything. Let's say this distance is L. Now, what can we say about this field? The magnetic field is uniform, so what property must the electric field have? If it has the same value everywhere, if it doesn't change everywhere, and this is constant, what can you say about this term?
That it's also uniform?
That's also uniform, okay. So over this length, that field is uniform. So what is the relationship between electric field? What's the relationship between electric field and electrical potential? Do you remember?
It's the negative integral of E dotted with ds.
Yeah, so delta V, or let me write it this way. The electric field is minus the gradient of V, but if I just look at the magnitude, in this particular case, just that, right? In this particular case.
Yeah.
Now, why can I write this? Because the other day I said I can't do this. The other day I said when the flux is changing, I can't write this, but now I'm saying that I can. Why is it?
Because if the flux is changing, then the magnetic field is changing, so we can't like. Is it because we can't say what direction the voltage drop is pointing in at that point if it's a non-uniform field?
Well, you said two different things there. The flux is changing, but what's not changing? The magnetic field is not changing, right? B is constant still. In all the examples I did the other day, not only was the flux changing, but it was changing because of the magnetic field. If you have a changing magnetic field, you're going to get a time-dependent electric field. This electric field will not be time-dependent. This electric field will be time-independent, so I can write it that way. Okay? This is a time-independent electric field. So then I can write this relationship. What I talked about on Tuesday, because B changed, E was time dependent. Because B was time dependent, E was time dependent. Here, B is time independent, E will be time independent, and I can write this. Thus, delta V that's induced, or motional, the magnitude of it is just going to be what? Well, I need to figure out what this is first. Well, V is perpendicular to B, so the magnitude of this, actually I shouldn't call it E induced, I should call it due to the motion of the rod. So E motional, I know it's kind of a weird name. The magnitude of it is just V times B. What's my delta X? Well, it's the length of this rod. So my motional EMF is basically the speed of the rod times B times L. The magnitude, I have it over there, the magnitude of the motional electric field is V rod times B. This is constant in time because B is constant in time. So I can write this relationship. Okay? Yeah, this one is conservative. If I integrate around the loop, I'm going to get 0.
Can you maybe briefly explain the time independence resulting in being able to put the negative sign there again?
It's not the negative sign, it's that it's equal to the gradient of V.
Oh, okay. That makes a lot more sense. I thought you were trying to tell me why you could put a negative sign there.
No,
Okay.
no, just this whole thing, right? I mean,
Right. Okay. Yeah. Thank you.
yeah, we can't, if the field is time dependent, I can't say E is minus the gradient of V. There actually has to be another term there.
So what would happen if the rod was at an angle?
If it was at an angle,
Yeah.
then I would write V cross B, then there would be a sine of theta in here.
Oh, okay.
Well, actually, you mean this angle?
Yeah, like the rod between the...
But the angle between the velocity vector and the magnetic field is still 90, though, in that particular case, right?
Yeah.
Okay. But if the rod had, well, if this frame was twisted, and so the rod was, let's say, rotated into the board, that's what you're looking at, right? If it was twisted in the board, then what's the magnitude of this cross product? Well, it'd be a sine of theta, right? Whatever that angle is. Right, that's how you find the magnitude of a cross product? You remember that? From...
Yeah.
Okay, so then you would have that term in there. And I will allude to that a little bit later. You know, what if the angle's 990? You brought it up. So then you would write the electric field as this, and then the magnitude electric field then would be, you just get something like this. Okay, but in that particular case, theta is 90. And in reality, then you would have to integrate around the loop to get delta V. Okay. So this is the motional EMF, and so what will happen is if it's large enough that light will go on, I'm going to have a current in my circuit, and I can calculate the current. It's pretty easy because I use Ohm's law. So then, I this induced or I motional is going to be delta V motional over R. And so that's going to be B times L times V of the rod over R. So again, this is the motional EMF. Sometimes we use script E with the subscript motional. So a lot of times it's written like this. And we write it like this a lot of times just because it's due to a changing flux. Okay. Are we okay so far? And maybe let's put some numbers into this. I'm going to put some numbers, and I'm going to ask a question. Why must the current be that way? Number one. Number two, the fact that this rod is moving to the right, and now there's a current induced because it's moving to the right, will there be a force on that rod?
Yes.
Yeah, you're right. There is. There's two reasons. There's two reasons for it, or there's two ways of looking at it.
The way I looked at it was just that the velocity vector is not parallel to the magnetic field, right? So there's definitely going to be a force on it, and it's got charge carriers inside of it.
Yeah, that's right. So you have a current going that way, right? You have a rod in a magnetic field.
Yeah.
Okay. Let's look at it two different ways. And I'll look at it your way second. Suppose I just took this rod, just gave it a push. Okay? I just gave this initial push and let it go. Light goes on. Where is the light getting its energy?
From your push?
Well, but I let go. I give it a push and I let it go, right? At any time in its motion, where's this getting its energy from? This has energy, right? If it's on, isn't it getting energy?
Yes, yes.
Okay. This is moving, right? By itself. I'm not pushing on it.
So is the kinetic energy of the rod turning into energy for the bulb?
Yes, that's what I'm trying to get at. So what's happening to the rod then?
It is losing kinetic energy?
Which means it...
Gains potential energy?
does it get faster or slower? Let me answer that.
Slower.
It gets slower. Okay, so it slows down, right?
Yeah.
So that means there has to be a force to the left. Right?
Yeah.
Okay, so there's a force on the rod to the left. It's got to slow down. Okay, that has to be true. Why? Why can't there be a force to the right?
Because then you would get infinite energy out of it.
Yeah, you'd have a perpetual motion machine, right?
Right.
Okay, so we're conserving energy. The force has to be to the right. Okay, because it's losing its energy and it's giving it to the light bulb so the light bulb can go on. So we do have a force to the left. Now, what's another way to look at it? Well, we have a rod in a magnetic field, and there's a current going through it, which you call I induced. And of course, we can use the equation F equals IL cross B to determine that force. And this I is the emotional or I induced. These are perpendicular to each other, so then F is ILB. That's too long a subscript. Okay. Now think about it. I have a magnetic field into the board, and I'm saying the force I'm saying the force has to be to the left. It cannot be to the right. Right? The physics says the force has to be to the right, to the left. Otherwise, this thing is going to speed up. So, which way must the induced current be? Mustn't it be upward? If I use the right-hand rule, my thumb points to the left that way. This just tells me the force has the induced current has to be this way. It has to be counterclockwise. Isn't it true?
Yeah.
Okay. It's all consistent, right?
Yeah.
So I can calculate this force a couple different ways. So let's put some numbers into this problem. Let's let the length of the rod be 1.6 meters. Let's let B, and these are a little bit unrealistic, 0.8 Tesla. And let's let V of the rod be 5 meters per second. So if we calculate the motional EMF, it's going to be 0.8 volt, 0.8 Tesla. I better not put the units in, I'm going to run out of space. The length of the rod is 1.6 meters. And V is 5 meters per second. So 5 times 1.6 is 8. 8 times 0.8 is 6.4. The current then, let's say the resistance of this bulb is 96 ohms. So then my current, I'm just making up these numbers. My current then is going to be 6.4 volts over 96 ohms, which comes out to 0.067 amps. Now, I know the volt, and this is the emotional voltage, current. Now, I know the current, I know the voltage, I can get power. Power is delta V times I. We know that. So I'm going to get 6.4 volts times 0.067 amps. That comes out to 0.43 watts. And in 1 minute, 60 seconds, remember these are joules per second, in 1 minute I'd use up 26 joules. So this thing is going to lose 26 joules per minute. So it's going to slow down. And without using this stuff, I can calculate the force that's required to keep it going at a constant velocity. In fact, I can calculate the force that's acting on this thing. Because F is constant. Because V is constant and I is constant. F is going to be constant.
Does that mean that at a certain point the rod will start moving back to the left?
Oh, that's a good question. But what happens when this comes to a stop?
Oh, then there's no longer a positive flux.
The flux stops changing, right?
Yeah.
So that means it's going to just come to a stop, right?
Right, yeah.
Yeah, so yeah, that's a good question. It's just going to come to a stop and that's it. It's going to lose all its energy. And we're going to calculate, we're going to derive in class today, we will derive an expression for V as a function of time. We're going to pretend there's no friction between the rod and the rails. Okay, so do you remember this equation from Physics 205 that power is instantaneous power is force times velocity? You remember that equation?
I'm going to be honest, no.
Okay, well here. Work is F dot dr. Remember
Yeah.
this? But dr is v dt, right? Isn't it true?
Right.
And then it
Yeah,
divides
yeah.
both sides by dt.
Right.
And so it's F dot V, which in this case is just F times V. Okay, so then the force is going to be the power over V rod. The power is 0.43 watts. The speed of the rod is 5 meters per second. And so the force on the rod, I should say rod, is this value. So just this, it can tell you what the force on the rod is. But let's go to the other board and calculate it a different way. Let's calculate it this way because I can, because I know what the motional current is. It's 0.067 amps. L is 1.6 meters and B is 0.8 Tesla. Guess what you get when you calculate this? You get the same thing.
Does it bother people, like physicist people, that Faraday's law can't be like derived, like that it can only be shown experimentally?
Well, no, I mean, you can't derive Newton's second law either, right?
Yeah, I guess that's true.
Yeah, and you really can't derive Newton's law of gravitation. I mean, for many years, Kepler's laws couldn't be derived, although Newton showed that you can derive them. We just don't know enough, I guess, that we can't derive those equations. And maybe it bothers some people, but not everybody. It could be that our theories are not. We don't understand things well enough that we can derive Faraday's law or Newton's second law. It's possible.
Right.
Because, yeah, there have been times, I mean, because Kepler's laws, they're called laws because at the time they couldn't derive them, but now you can. So yeah, I mean, it might bother some physicists, that's true. So are we okay with this so far? The fact that the current points in this direction is important. Okay. The direction of the current that's induced here satisfies the law of conservation of energy, and it's related to Lenz's law. Lenz's law, remember when I wrote down the expression, that minus sign was due to Lenz's law. Lenz's law has to do with conservation of energy. And so how do we express it in terms of, in regards to this changing flux? How is it related to this changing flux? In the last example I did the other day, I kind of alluded to it, and in this example, the direction of the current produces a flux that opposes the increase. So let's take a look at this. The rod moves to the right. The flux is increasing. The induced current produces a magnetic field that points out of the board in the opposite direction of this field. So it's going to produce a magnetic field that's opposite to this direction. So as the rod goes that way, it's trying to maintain status quo. Okay? Lenz's law wants to maintain status quo. It says that the flux wants to maintain status quo, so it produces a magnetic field in the opposite direction. Because otherwise, this thing would accelerate. If the current was in the opposite direction, this thing would just accelerate indefinitely. You'd violate conservation of energy. So again, Lenz's law states that the direction of the induced current in a circuit produces a magnetic force in the wire that opposes its motion. More generally, the induced current in a circuit opposes the change in flux. The fact that the current goes in this direction, it's counterclockwise, it produces a magnetic field out of the board. That means you have a flux increasing out of the board instead of into the board. It's trying to counteract what's happening here. That's Lenz's law. You have to understand Lenz's law. I will have some examples of Lenz's law in class today. In fact, I will have a demonstration of one. I wish I can do the other one. So, in regards to Chris's question, what if the magnetic field is not perpendicular to the velocity of the bar? Then you have to use this for your, and there's a minus sign missing in my equation, for the induced EMF, or the motion, and I should say motional EMF. So I should write this as motional. And then you'd have to integrate around the loop to get the motional EMF. So this is the motional field, integrate around the loop to get the motional EMF. By the way, nobody's brought up the question, does it bother you? Does it bother you that, the charges are moving here because of the magnetic field? Does it bother you that we have charges moving because of the magnetic field? What's doing the work? Is the magnetic field doing the work?
No.
What's doing the work?
Well, fields don't do work, right?
Well, magnetic fields. And we gotta be careful. Magnetic fields don't do work on charges.
So then wouldn't it just be the electric field that it creates?
Yeah, where's the electric field coming from? It's coming from me pushing the rod. Right? If I keep this thing going at a constant speed, right? If I apply the force of 0.086 newtons to the right so that this thing stays at a constant speed, I'm doing the work to make these things move. And you can show that. I have a slide in your notes. A lot of times I don't have time. Usually I don't have time to go through it, but I might at the beginning of class draw the picture on the board and show you what's happening. So you can see that it's the rod the fact that the rod is being pushed that's causing these things to move. If I give the rod just a push and let it go by itself, then the rod's going to lose its velocity. The energy is going to come from the energy in the bulb is going to come from the fact that the rod's moving its kinetic energy. But if I make this thing move at a constant speed, then the electrons are getting the energy from me pushing the rod. Does that make sense? So what we've seen so far is we can induce, or we can change a flux. We can have a changing flux either if we have a circuit that's moving or a circuit that's changing shape, or we have a time varying magnetic field. If you take this expression and you use a Leibniz rule for differentiating an integral, which you've seen, but also you got to use some of the rules for Calc 3. You'll get the following. You will get the following. You will get this is the velocity of the rod. You can actually break up this expression into two parts. This is due to the motional EMF. And this is due to induced due to time varying magnetic field. And of course, this is just taking the derivative of the time-dependent part of B, because it's a partial derivative. Okay? And so when the magnetic field changes, this contributes to the integral. When only the circuit moves, then this contributes to the integral. Of course, if both happen, then they both contribute to the integral, to this thing. Right? Because remember, this guy is minus the total derivative of that. Now, for our moving circuit that we were doing, we can apply this equation to this moving circuit. We can take the integral of B dot NdA here, but our dA is going to be this distance times dx. And so when you're just going to integrate over x, the integral of dx gives you x. And then when we take the derivative of x, you get dx dt, which is the velocity of the rod. And that comes from this term. Not this term, because this term is constant. The magnetic field is constant. So the motional EMF comes from this term, but you can see it and just directly applying it here, or doing it this way.
What you just wrote is only true if the field is uniform with respect to x, right?
This one, right?
Yeah, because if it wasn't, then you wouldn't be able to pull it out of the integral and just get x. Correct,
right? Because I'm doing it specifically for this example.
Right. Okay.
Yeah. So the slide that you see is for the wire moving on the rail. And by the way, no matter which reference frame, first of all, which I forgot to mention earlier, here's a rod. No matter which reference frame we're either in the frame of the rail or the rod, that light's going to go on, right? You both have to observe the same thing. If I view this, if the rod's going to the right, if I view this from the frame of reference of the rail says, oh, the rod's moving to the right with some speed v. According to the rod, the frame is moving to the left at the same speed, but the result is the same thing. It better be. So to summarize, EMFs either come from moving circuits or they arise from changing magnetic fields. In the case of moving circuits, you do need to have a physical circuit. In the case of changing magnetic field, the induced electric field requires no wires. If you do put a wire in that induced electric field, then what's going to happen is the electrons are going to experience a force and they're going to move around the loop in the wire. And so we have two different laws that can explain how EMFs are induced. By the way, I just stated this here, and like I said in the slide, you can use Leibniz rule for differentiation and vector calculus to derive this. However, one of the videos I put in the module, the instructor, he's the guy from Yale, he actually derives this without using Calc 3. The only thing is the arguments he uses might be a little bit, hopefully not too confusing for the class. It might be hard to see what he's doing, but it comes out very nicely. If you understand what he's doing, it comes out very nicely. It's kind of cool what he does. Okay, so if you're interested, you can watch him derive this. But I think he has a minus sign in one of his equations. Or no, I'm sorry. I was thinking a different video. Never mind. His are correct. So watch his video if you have a chance. He actually does it. There's one video where he talks about Ampere's law, and then after that he talks about Faraday's law, and he actually derives this. But the derivations might be a little bit difficult for you, just to let you know. Okay, I just don't have time to go through a full derivation using his methods. There's too many. There's details I'm leaving out just because of time. Questions? Concerns?
I have a question about the expression for the closed loop integral, where you have delta v is equal to the line integral or path integral of v cross b dotted with dl. Do you know which one I'm referring to? Where does the v cross b part come from?
Well, isn't it true that when the electrons go to the right, when the rod goes to the right, the electrons are moving down, right?
Oh, okay. And it's just what creates the field.
That's what creates the field, because we said that the electrons are going to accelerate until E is minus V cross B.
Right.
And that's where it comes from. That tells what E is then.
Okay, cool. Thank you.
Sure. Other questions? So Damien, you had a question on the worksheet. What was your question?
Yeah, so I was going through number 2, and I was doing the here, let me pull it up really quick, because I don't want to, since I'm not showing it to you, I want to make sure that I say things correctly. I was doing part C, which is writing the expression for the unit vector R. And I did it differently than the way you described doing it in the office hours, and I feel like I'm doing it correctly, but I get an expression that's different. I'm really close though. Like if you use the half angle formula on the R hat you get from doing it your way, then you end up with something really, really similar to what I got.
What did you get for R hat?
So actually, I think it might be more useful if I just tell you how I set it up, because it's actually pretty simple. I just said that the y component of the, so I started by creating an L vector that goes from any point on it to the origin, and then I divided it by its magnitude so that I could make it a unit vector.
Okay.
And the y component is just b, the distance from the origin to the center of the ring, you know. And then you do the sine of theta gives you the height above that, like inside the ring. You know what I mean?
So you took B and added something to it.
Yeah, I took b and then added b sine theta.
Okay, that's fine.
And then for the x component, it's just going to be b cosine theta since there's no additional, you know, movement to the left or right.
Okay.
And then if you take its magnitude, you know, you square b cosine theta and then square 1 plus, or, you know, b plus b sine theta and put it all under a square root, blah, blah, blah.
Yeah, that's fine. I mean, that's fine what you did.
Okay, I was just curious if it was because you know it looks different than the way the answer you get from doing it the way you were talking about, and obviously I know that doesn't necessarily mean they're different, but I wasn't really finding a way to mathematically show they're the same.
Yeah, because this is what I got. And of course, we can rewrite this different ways, right?
Yeah, of course.
And the reason why, because I was able to show that phi was equal to pi over 4.
Yeah, that's exactly what I have too. I derived it both ways, and I ended up using it that way just because A, the expression is simpler, and B, it takes less like actual math to do it that way.
Yeah.
So I went through the problem doing it that way. I was curious why mine was like similar but didn't look the same, you know?
Probably I would have to use some sort of identity to rewrite it.
Yeah. I tried for like 10 minutes, but then I gave up because it just seemed pointless.
Okay. It'd be interesting. Yeah, it'd be interesting to do it the other way. It is more work.
Yeah, it's not super complicated, but it's definitely more work, yeah.
Yeah, it should work. As long as you don't make a mistake, it should, what you said was correct, so.
And then for that same problem, would you mind going through deriving the ds vector?
So let me draw the picture. Wait, let me erase this and draw a bigger picture. What else did I draw? I didn't draw that. That's a theta. So ds. Oops. Let me use red. Too many markers. ds is that, right? It points to that they're a tangent to the circle.
Yeah, always, yeah.
And the I'll draw it on this side, but this is just the arc length, right?
Right.
So the magnitude of ds is equal to just, this is b d theta.
Right.
So what is the direction of this vector? That's what we want to know, right?
Yeah, I drew a whole bunch of angles, and it has something to do with cosines and sines of theta, right?
Yeah, so I just gotta break this up into x and y components. This is really not a good picture, but
The only reason I'm asking is because I did all of this, and I think I'm going to get the same thing that you got based on the way that you're going. And I tried plugging the integral into a few different integral calculators, and some of them like literally could not perform the integral. I had to break it into two separate integrals and then do them each individually.
this should end up being theta, right?
I actually got the other angle in that triangle being theta, but I could be wrong. I don't know.
Yeah, I didn't draw this very nicely. And this ends up being 90 minus theta. And so ds and both of them are positive, right?
Yeah. Yeah, I had cosine in the I hat and sine in the J hat, so I'm wondering if that's why maybe that made the integral like 10 times harder, you know?
Yeah, it depends on how you write it. I mean, my integral, my dB looked like this. And some of you folks are good at doing these integrals, so. I had to use some angle addition formulas to get to this point. And then I just did it on Wolfram.
Oh yeah, I guess the top of my fraction is like the double angle formula or something for one of them.
Yeah, well, I had to use an angle addition formula after I did ds cross r hat.
Right, yeah, I'm just looking at it again and I'm noticing that it definitely does look like an identity, yeah.
I didn't simplify this, but I mean, that's initially what I had. And then I just did integral on Wolfram.
Gotcha. So I just needed to simplify it more. I still ended up getting an answer, but it was just kind of took me more work than it should have, I could tell.
Okay, yeah. And typically when people do this problem, they might have this in a different form, but you should get the same result.
Right.
Because I saw this angle here, I didn't want to bother. I was like, okay, I'm not going to mess around with that. I'm sure you can rewrite this so that you can use another angle addition formula to rewrite this so you can actually do the integral. But you were saying it wasn't giving you an answer.
Well, it wasn't when I typed the whole integral in, but there was a plus in between my two terms, so I just split it into two separate integrals, and then it was able to do it.
Well, that's weird.
Yeah, I didn't simplify it nearly as much as I could have, so I think that was just the issue.
Yeah, I'm wondering why Wolfram didn't like it. Oh, well, yeah, I don't know. I mean, I don't know. Maybe sometimes, those software is not perfect. So
Yeah, I just think that I didn't set it up very well either.
if it's right, it's right. I guess. I mean, if you did it right, that's fine. If you did it correctly, that's okay. Sure, no problem. Damien. Other questions? If not, I will see you at 2. Thank you.